Welcome to today's class on differential geometry. Today we discuss orientation. First we define orientation. A smooth unit normal vector field. A smooth unit normal vector field on an n surface S in Rn plus 1 is called an orientation on S. An oriented n surface is a surface together with a choice of orientation on it. Together with a choice of orientation on it. We discuss a theorem. A connected n surface in Rn plus 1 has exactly two orientations. So we prove this proof. Let S be a connected n surface. Then S is equal to F inverse of C, where F is a function from U to R, where U is open in Rn plus 1, such that del F of P not equal to 0 for all P in S. Now define n1 of P as del F of P divided by norm del F of P for all P in S. Then you know that n1 is a smooth unitary normal vector field on S. Then n1 is a smooth vector field on S, and SP per is span of n1 of P, as you know. Also, norm of n1 of P is equal to norm of del F of P divided by norm del F of P. So that is equal to 1. This is true for all P in S. And you know that since SP per P is the span of n1 of P, n1 of P belongs to SP per. That is, n1 is an orientation on S. You have n1 belongs to SP per and norm n1 of P is 1. Therefore, n1 is an orientation on S. Similarly, n2 of P is equal to minus del F of P divided by norm del F of P is another orientation on S. Now we show that these are the only unit normal vector fields on S. If not, let N3 be another smooth unit normal vector field. Another smooth unit normal vector field on S. Then SP perp, you know that SP perp is a span of N1 of P. This implies N3 of P belongs to span N1 of P because both are unit normal vector fields. So this implies N3 of P equal to some lambda times N1 of P. And this is true for each P in S, which is true for each P in S. Thus, we can define a map G from S to R by G of P equal to lambda, that is equal to N3 of P dot N1 of P. So from here you can see that N3 of P dot N1 of P is lambda, because lambda into N1 of P into dot N1 of P, so that is 1. So this is lambda. So you can define a map G from S to R by G of P is equal to lambda, that is equal to N3 of P dot N1 of P. Clearly, G is smooth and N3 of P is equal to G of P times N1 of P. That is from here. Now this implies norm of N3 of P is equal to modulus of G of P into norm of N1 of P. You know that norm of N3 of P is 1. This is true for all P in S. That is modulus of G of P equal to 1 for all P in S. This implies G of P is plus or minus 1. Now, since S is a connected end surface, and G is from S to R, such that G of P is equal to plus or minus 1 for all P in S. By our previous example, G is a constant. By example 1, G is a constant. And we have seen that G is identically equal to 1 or G is identically equal to minus 1. This we have done. So from here, N of P, therefore N3 of P is G of P into N1 of P implies N3 of P is plus or minus 1 N1 of P. That is, N3 of P is either N1 of P or n3 of p is minus n1 of p, that is actually equal to n2 of p. Therefore, S has exactly one orientation. This is for all p in S. Therefore, n1 and n2 are the only orientations on S. That is, S has exactly one orientation. This proves that theorem. Now we give some examples. Example 1. The Mobius band is an example of a non-oriented surface. Mobius band in R3 has no orientation. There does not exist a smooth function f from U to R such that M, the Mobius band, equal to f inverse of C and del f of p is not equal to 0 for all p in M. So this is M, the surface M. Therefore, according to our definition, M is not a surface, but we call the Mobius band M as an unorientable two surface. So from this video, you can see that the Mobius band has no orientation. So you cannot define a smooth unit normal vector field. Now we do another example question. Show that two orientations on the n sphere, x1 square plus x2 square plus etc. plus xn plus 1 square equal to r square of radius r greater than 0 are given by n1 of p is equal to p by r and n2 of p is equal to p minus p by r. So solution, let Sn of r is set of all x1, x2, etc. xn plus 1 such that x1 square plus x2 square plus etc. plus xn plus 1 square equal to r square. Then Sn of R is a sphere of radius r in Rn plus 1. Define f of x1, x2, etc. xn plus 1 equal to x1 square plus x2 square plus etc. plus xn plus 1 square. Then Sn of r is f inverse of r square. Let P be the point x1, x2, etc. xn plus 1. Then del f of P is P 2x1, 2x2, etc. 2xn plus 1. That is actually equal to P 2P. Norm del f of p square. You know that this is equal to del f of p dot del f of p. So this is 4 into x1 square plus x2 square plus etc plus xn plus 1 square. So this is 4 into r square, because x1 square plus x2 square plus etc xn plus 1 square is equal to r square for p in S. You know that p is an element in S. So this is an element in S for r square. Therefore, norm del f of p is equal to 2r. Now, by a previous example, you have seen that S is connected. So since the n surface Sn is connected, of R is connected, by previous theorem, the orientations are n1 of p Sn of R are n1 of p and n2 of p, where n1 of p is del f of p by norm del f of p and n2 of p is minus del f of p by norm del f of p. So here, therefore, n1 of p equal to, we know that norm del f of p is 2r. So this is 1 by 2r p 2x1, 2x2, etc. 2xn plus 1. So this is equal to 1 by 2r p 2p. So this is equal to, at p, 2p by 2r. So this is p by r. And n2 of p equal to minus del f of p divided by norm del f of p. So that is minus 1 by 2r p 2p. So you will get this as at p minus p by r. Therefore, the two orientations on Sn of R are p by r and p minus p by r. On a three surface R4, an orientation can be used to define a sense of handedness in the tangent space at each point of the surface. Given an oriented three surface S and a point P in S, an ordered orthonormal basis E1, E2, E3 of the tangent space SP to S at P is said to be right-handed if the determinant E1, E2, E3, n of P is positive. So it is right-handed if the determinant of this matrix is positive, where n of P is P n of P is an orientation normal direction at P. EI is PEI for I equal to 1, 2, 3. The basis is left-handed if the determinant is negative. Now, on an n surface in Rn plus 1, n is arbitrary, and orientation can be used to partition the collection of all ordered bases of each tangent space into two subsets, those consistent with orientation and those inconsistent with the orientation. An ordered basis V1, V2, etc. Vn, not necessarily orthonormal, for the tangent space SP at the point P of the oriented n surface is said to be consistent with orientation n on S if the determinant V1, V2, etc. Vn, n of P is positive. The basis is inconsistent with n if the determinant is negative. As usual, V is PV, Vi is PVi, and n of P is P n of P. Vectors acting at P and normal vector acting at P. So the tangent space SP at the point P is said to be consistent with orientation if this determinant is positive, and inconsistent with orientation if this determinant is negative. Now we do a problem. Let S be an oriented n surface in Rn plus 1 with orientation n, and let P belongs to S. Show that an ordered basis for Sp is inconsistent with n if and only if it is consistent with minus n. So solution. Let V1, V2, etc. Vn be a basis, be an ordered basis Sp which is inconsistent with n. That is determinant of V1, V2, etc. Vn n is less than 0. Now this is if and only if determinant V1, V2, etc. Vn minus n is greater than 0. That is if and only if Sp is consistent with minus n. So this solves that problem. So this is if and only if the ordered basis for Sp is consistent with minus n. That is, the ordered basis for Sp is inconsistent with n if and only if it is consistent with minus n. So this solves that problem.